Right, so let me first thank the organizers for this beautiful meeting, for inviting me to give this talk. And I should have a pointer, and it's over here. There we go. So I will talk about machine learning of Calabi Yau geometry and of Ritchie-flat Calabi Yau metrics in particular. And this is work based on work that I've done in collaboration with Andre Lucas, Fabian Ruhle, and Robin Schneider, Lara Anderson, James Gray, and Jakob Hendy and Moritz Walden. And it's partly published and partly in progress. And I should say that while we have worked on this in our collaboration, so have many other people. So what I'll try to do in this talk is not only to present the work that we have done, but also other attempts to resolve this, to find a Ritchie-flat metric on Calabi Yau geometry using machine learning and other tools. So I hope I will have time to give you some flavor for what this research is about and what kind of tools are being used, but I will not go into many details. So why should we use machine learning in string theory? This is something that we will hear about now this morning, and then there will also be an exciting talk this afternoon about the prospects of machine learning. So in general, why we are interested in machine learning is because it provides tools to do things that we may not want to do, because these are mundane tasks that we want to have a machine do instead, like labeling what kind of pictures we see in some library, or some complicated tasks that we might need the machine's help to do, so like play the game of Go, here, which is shown here. Or, as I'm sure you're all aware of, we can use machine learning to, as a sparring partner, as something that can help us do things by providing, by synthesizing information from large text collections that it has learned from, so in large language models. And the success in these methods is driven by different developments, different technical developments that I will not go into detail about, but what I want to mention to you is that there are very user-friendly machine learning libraries that we can use in our community to attack the questions that we are interested in. And this is what has been done so far. So in string theory, we might want to use machine learning to attack different kinds of questions, and these are just some examples of topics that people have studied using machine learning in recent years. So building string vacua in the string landscape that match certain criteria, be it producing a standard model of particle physics or achieving other interesting phenomenological properties, is something that machine learning can be used for and has been used for. In the swampland program, we can use machine learning to test swampland conjectures in different settings. We can also hope to use machine learning and its ability to classify and find patterns in data, in large collections of data, to actually get ideas for new swampland conjectures. This has not been done yet, but it might be something that could be done in the future. What I'll talk about today is using machine learning for numerics. So I want to use machine learning to compute approximations of Ritchie-flat metrics on Calabi Yau manifolds, and this is one example of where we might want to use numerics in string theory. Another example is the conformal bootstrap program. If we go a bit outside of the field of string theory, there are other questions that we might ask. So we might look for mathematical structures using machine learning that may be of relevance for physics, or we might use our intuition as physicists to explain how machine learning works, or and this is a field that is very active. And I've listed some reviews here, so if you're interested in this, then going to these sources will give you more details. So let's then go to the main topic of this talk, which is Calabi Yau geometry. So what I want to do is that I want to find approximations for the Ritchie-flat metric on Calabi Yau manifold. So we know by the Calabi Yau theorem that such a Ritchie-flat metric exists, and it is unique. So given a Kähler class, there will be a unique Kähler form that corresponds to a metric which is Ritchie-flat. And this is what I will call the Calabi Yau metric in the remainder of this talk. However, there is no analytical expressions for this Calabi Yau metric in non-trivial cases. And why is that? Well, it's because it's a difficult equation to solve. So if we want to solve the condition of Ritchie flatness, then this is a fourth-order nonlinear PDE on a non-compact complex scalar space. So this is a very complicated equation to solve. However, from the Calabi Yau theorem and Yau's proof of the theorem, we know that we can translate the condition of Ritchie flatness into a second-order partial differential equation for a function, a global function, phi, and this makes it more tractable to approach this problem numerically, as I will explain. So how does this work? Well, we know that since the unique Kähler form that corresponds to the Calabi Yau metric is in the same Kähler class as some reference Kähler form that we may just pick, then we know that we can write the Calabi Yau Kähler form that we're after in the form here. So it's an exact piece added to the reference Kähler form. Moreover, in Yau's proof, he wrote down this complex Monge-Ampere equation, which can be translated to this second-order partial differential equation for the field phi. So what we can do then numerically is that we can sample points on our manifold, on the Calabi Yau manifold. We can compute these reference forms, so we can, using the information that we have, we can compute this reference form J. We can also compute this holomorphic top form omega here. And we can compute this constant kappa using the information that we have from the sample of points. And then we can use that to solve the Monge-Ampere equation numerically. And this is something that we can, of course, attempt to do with different methods. So for since 2005, this has been explored with numerical methods. That's almost 20 years now. And the first methods were based on Tian's realization that you can write Calabi Yau metrics can be, or approximations of Calabi Yau metrics can be given by algebraic metrics, where you expand the Kähler potential of this metric in terms of a basis of polynomials of a certain degree. And if you take the degree of these polynomials to infinity, then you get a complete basis, so then you get an exact expression for the Calabi Yau metric. So I will refer to these methods as being based on, as using a spectral basis, because this polynomial basis is a spectral basis on the ambient space for the Calabi Yau. And then in methods using these algebraic methods, then you solve for this, for a matrix here, H, which contains the coefficients of these expansions. So one can do that using different methods. The first one is due to Donaldson, so that's Donaldson's algorithm. Then one can use functional minimization, which gives a very good accuracy for a given order k. Or one can use machine learning. And in the recent years, we've seen a lot of progress from the machine learning. Now, in machine learning, there is actually no need to use this particular expansion of the metric or this particular form of the metric. One can do so, but one do not have to do so, because there are theorems in theoretical machine learning that tells you that neural networks, which is the basic component of these machine learning methods that we use, they are universal approximators, which means that they can approximate any function if they are complex enough. So if we make them wide enough, we have enough parameters in our models, then we know that we can get an approximation for any function. And this is very, very useful. So we can actually use then these neural networks to directly approximate the metric or this function phi if we want to. So the workflow that we have then is that we will construct some sample of points on our Calabi Yau manifold. This will depend on the moduli of the Calabi Yau. So when we define the example geometry that we're studying, then we have to specify the Kähler and complex structure moduli of the Calabi Yau. Then we will set up a machine learning model, which will include a neural network. We will train this model using loss functions that I will define and some training algorithm to get a good prediction for the Calabi Yau metric. And then we will check this prediction using error measures, which have been used which are standard and have been used for these other numerical methods as well. So how do we do this? Well, the first thing then is to generate a point sample. This is not really machine learning, but it's something where people have worked also in recent years, so I wanted to have one slide on that. So we have a Calabi Yau manifold. We need to pick a particular example. So starting with the simplest case of constructing Calabi Yau manifolds is if you take to define your Calabi Yau as a hypersurface in a compact complex ambient space, and the simplest compact complex ambient spaces that we know of are the complex projective spaces. So for example, the quintic, which is depicted here, is an example of a three-dimensional Calabi Yau manifold given as a hypersurface in P4. And Douglas and collaborators developed an algorithm for how to sample points on such manifolds some time ago. So what you do is that you sample 2 points on your ambient space, you connect them with the line, and then this line has a parameter, and you use the polynomial that defines your Calabi Yau hypersurface to solve for the parameter of the line. So you intersect the line with the hypersurface, and that gives you then n+1 points on your Calabi Yau, if the Calabi Yau is an ambient space in Pn. So there's a mathematical theorem by Schiffman and Seldich telling you that if you do this, then the points that you sample will be distributed with respect to a known measure, which is the Fubini-Studi volume measure on the Calabi Yau. And this is something that we need to know because in the end, we will use these points to compute integrals. And when we compute these integrals, we need to know with respect to which integration measure we should integrate things. So we need to sample points randomly on the Calabi Yau. We need to have a lot of points so that we're covering the whole space. And then we need to know how they are distributed. And this is something that this algorithm gives us. And the algorithm has been generalized to other manifolds, complete intersection Calabi Yaus, and Calabi Yau hypersurfaces that have toric ambient spaces from the Kreuzes calculus in recent years. Also, this method has now been included in the machine learning packages that have been written for this particular problem, the Calabi Yau metric problem. So these point generators are already implemented, and they work, and they are super fast. So this is a problem that has been solved very nicely. So then we use this point sample that we have. We take that as in data into a machine learning model, which will be some neural network. It can have different architectures, but it will always have an input layer where we take in the point sample and maybe some information about the moduli if we want. Then we have an output layer, which gives us the prediction. So this should be either the Calabi Yau metric or its scalar form, or this function phi. And then in the middle here, something is happening. This is the thing that we will train, and I'll come back to that in 2 slides. But first, we can start here and think about, okay, what is it that we want to predict? Do we want to predict this function phi, or do we want to predict the metric directly? There are different reasons for the choices that we might make. So if we predict the function phi, then we know that we will automatically get a Kähler metric, so that's very nice. We are then guaranteed that this will be Kähler. But if we just predict the metric, then this is something that we could perhaps use to go beyond the Calabi Yau case. So it gives something a bit more flexibility to our networks. Thank you. With that thought, so this is something that has been explored in these recent papers. So there are examples of algorithms that learn the Calabi Yau metric, that learn the Kähler potential or the function phi, and there are also examples of machine learning models that are based on Donaldson's algorithm and learns this matrix age of coefficients of this expansion of the Kähler potential in the spectral basis. And I've also written here, so here are some illustrations for what these implementations look like, and here are the packages that include these particular implementations. Okay, so once we have selected our architecture, we should train the model so that we get a good prediction. And the training is done by adapting these hidden layers here. So these nodes are connected to each other by linear transformations specified by some matrix A and some vector B. So this is some bias vector, and this is some linear matrix that takes us from one layer to another. when we train the metric, what we're doing is that we are adapting, we're changing these A's and B's to minimize something, and what we will minimize is called a loss function. There are also some nonlinear activation functions here in each of the layers, and these are important because otherwise this would just be a linear model that would collapse to just one layer. So we want to train the model to minimize some loss functions, and we do that using the methods that are available in these machine learning libraries, and it's stochastic gradient descent that is the leading method that's been used. So what do we want to achieve? Well, we want to get a Ritchie-flat metric, and we do not know what that Ritchie-flat metric is, so this is unknown. So we cannot compare in data with known out data, which is a standard thing to do in machine learning. Instead, what we do is something that is called semi-supervised learning. So we encode all the conditions that we want the metric to satisfy in loss functions. So there will be some scalar functions that encode the constraints that we want to satisfy. So for example, here for the Monge-Ampere loss, we want to satisfy the Monge-Ampere equation. So we compute for each point how much we are differing from the Monge-Ampere, from solving the Monge-Ampere equation, and then we sum that up and take the norm of the sum. If we have some metric, or if we have a machine learning model that is less rigid, so that does not give automatically a Kähler metric, for example, then we need to impose that as a loss function as well. Also, if we have a Calabi Yau manifold with more than one Kähler class, then we need to have a Kähler class loss function that makes sure that we stay in the same Kähler class. And then after training, we should check the accuracy. So we should compute these error measures that tell us how far we are from solving the constraints that we want to solve. And the ones that we're interested in the end, is in particular the Monge-Ampere equation. So there's the sigma measure is measuring that. It's the weighted. It's just an integral over this loss function again. And then we can also we can check whether we have a Ritchie-flat metric in the end. So and then there are other things that we need to check if we have more than one Kähler class. So then what do? We do experiments with this, and we check that this works on different examples. So what we can see when we're using these machine learning models is that they are less sensitive to having symmetric Calabi Yau manifolds. This was something that was required with previous techniques, and it's not needed anymore. So the performance is comparable on symmetric and not symmetric manifolds. And they also work in many more cases of manifolds because we have these new point sampling routines. And once we have the point sample, then the machine learning model does not really care too much about what kind of Calabi Yau we have, how it was constructed. We can also check the accuracy of these models, and we can compare it. In particular, if we work on the cubic, so on the one-dimensional Calabi Yau, we know what the metric is, and we can check how good the prediction is. And the prediction, as shown here in this plot, is fairly good. We can do changes to our architecture to improve the performance. So one can question this using just loss functions to enforce constraints. So I've already said that we can tweak our architecture to impose more constraints. And we can also include layers in our architectures that would improve performance and get more accuracy, get better accuracy. Thank you. Inspired by this, the fact that we can include such layers that improve our performance and make the prediction for our Calabi Yau metric more accurate and also on global terms, I've been exploring now in the past year together with my students how to use the discrete symmetries that Calabi Yau manifolds may have in machine learning models and how we can include that in a natural way. So we know that these discrete symmetries are crucial for the non-machine learning methods for numerical Calabi Yau metrics, and we wanted to explore what effect they have in machine learning. So symmetries in machine learning is a topic that is widely studied also outside of our field. Invariant and equivariant machine learning models are used and are very performant to do a lot of different tasks. And there's a lot of research in this field. And the way that you can include this in a model, if you want to have an invariant prediction, which is what you want to have if you're predicting this function phi, then you just need to include one layer that gives you this invariance into your model, and then all the full model will be invariant, as is shown here. So we have explored this to compute metrics on different kinds of Calabi Yau manifolds, and we find that including these symmetries does have a good effect on performance, but it's not as dramatic as it is for these other methods. It's simple to implement because we can implement these symmetry-preserving layers by using some ideas that have been published in the machine learning literature and the math literature recently, and so it's just layers that project our input data into fundamental domains of the group that that the data is symmetric under. And we see that this has some good effect on these loss functions. We do get a better training and test data, and it also has a good effect on the Ritchie loss, which is something that we do not use for training. So that's nice. It's something that can be used, and that can be used in other models as well. We have done this in a particular using one of these libraries, the CY metric library. Okay, there are applications where this has been used. People have computed physical Joukava couplings using machine learning and tested swampland distance conjectures, but I think I'm out of time, so I will skip these and I will go to my conclusion. So what I've told you is that we can use machine learning models to learn Ritchie flat metrics on many different Calabi Yau manifolds. The most popular constructions that we have for Calabi Yau manifolds are the CCs and the Kroitchi-Skarke Calabi Yau manifolds, and the machine learning methods work on all of these. The mathematical constraints will be encoded either into the architecture of the neural network or as loss functions, and one has to make a decision on how much flexibility we want to have when doing this. There are performant machine learning packages that are available to use and that can also be modified and adapted by users. So if you're interested in this, I really encourage you to look at these packages and play around with it a bit. There are physics applications that people have started to explore. And of course, there's much more that can be done. One can go beyond Calabi Yau metrics. One can look at more properties of Calabi Yau metrics, for example, the moduli dependence. And with that, I would like to thank you for listening.
Thank you very much, Magdalena. It's a very nice talk. Perfect timing also, very good. Questions? Kumrun.
Very nice talk. I'm just curious to know whether these techniques have been used to find the spectrum of Laplacian on Calabi Yau.
Yes.
And if so, how do they, and has there been a comparison to points that we can solve the Calabi Yau using conformal theories in the context of string theory? So I know that the answer does not need to be the same because of the string correction, but just interested to know the comparison of the spectrum. Has that been made?
I do not think the comparison has been made, but I'm not completely sure. So there are these papers by Anthony Ashmore and Fabian Rule and Fabian's PhD student, where they are computing these spectra, and they are looking at they're comparing with the swampland distance constraint. So these are the works that I'm aware of. I do not recall that they compare with with other methods, but it might be that I just missed that in the papers.
Okay, thank you.
More questions? David?
Thanks for the talk. Can you comment more on the Yukawa couplings and what's the status of this for particle physics?
Yes. Thank you for asking. Yes, so this has been computed in the heterotic field. So in the heterotic field, we know how to compute Yukawa couplings using the fact that the matter fields come from gauge bundles, we know exactly what things we need to compute there. So this is something that has been explored since the 80s, and we also know models where if we make a particular choice for the connection of the gauge bundle, known as a standard embedding, then we can compute the physical Yukawa couplings exactly. So in the heterotic setting, we can always compute the holomorphic Yukawa couplings, but then we need to do a field redefinition to get the physical Yukawa couplings, and that's the tricky bit that involves knowing something about the Calabi Yau geometry. So the standard embedding was checked in January this year by Butbaya and collaborators. And so the first plot here is showing the agreement between the numerical Yukawa couplings and the exact values. So it's a very good agreement. Then there was another group, Konstantin, Fraser Taliente, Harvey, Lucas, and Overett, and I think Fraser Taliente is here. Kit is here somewhere. I've seen him. And they looked at other. So the vast majority of heterotic models for particle physics do not use the standard embedding. They use other ways of constructing the gauge sector. And one is using, a very nice one is using line bundle sums. It's simple and gives a ton of models. So they are exploring that setting in their paper. And what they found, so what they used then is that they used machine learning to compute the Ritchie flat Calabi Yau metric, the Hermitian-Yang-Mills connection, and the harmonic representatives for the fields they're interested in. So that's a lot of different machine learning models that you need. I think they counted to 7 in the experiment that they did. And then they computed all of that, and they, in the end, produced this plot where they show what the trained network gives, what the reference metric gives. So this is using these reference forms that you have sort of for free from the Calabi Yau construction, and then what you would get from some canonical computation, and this is the result that they saw. So they saw that there was certainly an improvement of getting these trained metrics, but they also made an argument that maybe, since there are so many machine learning models that you need to train, perhaps you can also use these reference metrics as a first, if you're just doing some sort of first test of your model, then maybe you can actually just get by doing that. So that was a nice outcome of the paper to see how these things compare.
Yeah, thank you. Any question, Jack?
Has anyone approached finding solutions to the Hermitian-Einstein equations, the Donaldson-Uhlenbeck-Yau theorem? That's important for heterotic, right?
Yes. So that's something that we in particular both of these papers here they solve the Hermitian-Yang-Mills connection. I mean they solve the Hermitian-Yang-Mills equation for the connection using machine learning in both of these examples. And that is something that has also been, so I did not have a lot of references for older work on this, but this is something that has also been done using other numerical methods in the past.
Question?
So there is another more ambitious approach to this problem with neural operators, where you try to learn map from the initial data to final data directly by using many, say in your case, Calabi Yaus. Do you think has it been tried for this problem?
So I didn't quite catch what you said.
This neural operators, right? You know,
yeah.
Here you give initial data, then you do loss function, you get the solution. But imagine now you know many examples, and you assume that there is a map from initial data to final data. You can try to learn this solution map directly. And people tried it in Bootstrap, say, recently. Has it been tried in Calabi Yaus?
No, it has not. It's an interesting idea.
Thanks.
Good. Any questions from Zoom? No? Very good. So let's thank Magdalena again.